All right. The next topic in our discussion of finances and how functions play a role in finances so the next topic we're going to discuss is about annuities. So an annuity is a sequence of equal payments paid or received at regular intervals of time. Roughly speaking, you can kind of think of it this way: like if you wanted to put away a bunch of money to buy a car, for example, like you didn't want to have to go into debt to buy the car, so you're saving up money ahead of time to buy a car, right? And you decide to put away a little bit of money each month. The money in your account is going to accrue interest, but it's not going to be a case of just compound interest where you put in a lump sum and then it accrues interest, because you're going to continue to put in more and more money over a period of time, right? And that's more or less kind of the concept that we're trying to capture here. So, so I have two examples to kind of illustrate what an annuity is. So, example one. You want to accrue some desired sum of money in the future by making small deposits on a regular basis. The sum F is called the future value of the annuity. For instance, upon the birth of your daughter, you might want to deposit some fixed amount of money R each month for the next 18 years at 4.75% annual interest in order to accumulate $40,000 for her college education. You want to determine the value of R, the money that you have to deposit each month, right? So this would be an example of the type of problem that we would want to be able to solve. And again, it's going to require a little bit more tools than what we have right now, because this is not just a case where you're going to put away a lump sum of money at the beginning and then just sit around. You're going to be putting in money every month, right? So it's a little different. It's an annuity. Another example, you want to make one large initial deposit right now for the purpose of receiving equal regular payments over an extended future period. Like this is something that people who win the lottery do, right? So for instance, you might want to receive $3,500 at the end of every quarter for the next 6 years. And so you wish to know the present value P that you need to invest now at 8% interest compounded quarterly. So what makes these situations different from what we did in the previous lecture is that the amount changes not only because of the interest accrued, but because additional money is periodically put into or taken out of the account by the investor. Okay, so it's a little bit more complicated. It's a little more complicated, but it's also a little bit more like actual real life stuff, right? That's the thing. The closer you get to the real world scenario, the more complicated the mathematics becomes, okay? But anyway, the time period between payments made or received in any annuity is known as the payment period or interval. Each payment is called the rent. The term is the length of time from the beginning of the annuity until it has expired. So in example 1 up here, the payment period is 1 month, right? Because you're going to put away some amount of money R each month, right? So the payment period is 1 month. The rent is the unknown R, and the term is 18 years because you're gonna put away money every month for 18 years. Okay. In example 2, the period is 1 quarter because you want to receive payments at the end of every quarter, right? So the pay period is 1 quarter. The rent is $3,500, okay? And the term is 6 years, okay? In this lecture, we're going to discuss how to find the future value of an annuity and then how to solve for R in things like case 1. We'll talk about how to solve for P in something like case 2 in the next lecture. A couple of other terms to share with you before we look at some examples is that there are a lot of details about when the rent is paid and so forth, right? There are a lot of like nitty-gritty details. And if you were actually like a financial planner, then you would be concerned with all of those things. For the purposes of this class, we're only going to look at what's called simple ordinary annuities. And what that means is that the interest period is equal in length to the payment period. And payments are made at the end of the period, right? So if you have interest that's compounded monthly, then you're going to make payments monthly. And if you have interest that's compounded annually, you're going to make payments annually, right? So the interest period is equal to the payment period, and payments are made at the end of the period rather than at the beginning of the period or somewhere in between. Again, there are ways to handle those more complicated situations. We're just not going to worry about them in this class. And then one more thing, by the way, that should say the. So by the way, an annuity established for the purpose of accumulating a specific amount of money in the future is called a sinking fund. So in example 1, right, we wanted to accrue $40,000 in 18 years. So we would call this situation a sinking fund. Okay. I might come back to this second page. What this second page is a derivation of this formula that down here, which this formula tells us what the future value of an annuity is going to be. Well, actually, let's just run through it real quick before we get to the examples, because I only have 3 examples to show you, so this should be a relatively short lecture. But anyway, recall that this is the formula for compound interest that's compounded m times per year. This formula will give you the future value if you don't add any additional money into the account, if you don't put any more money into the account other than just what you put in at the very beginning. But imagine that instead of putting in some lump sum at the beginning, you put in a little bit R each month, or at the beginning of each payment period. Okay, so in the first payment period, the amount of money in the account is R. At the end of the second payment period, it's going to be R times 1 plus R over M, right? Because that's the amount that's the amount of the original plus the interest earned on the original. But then you also make an additional payment of R dollars, right? At the end of the third payment period, this will accrue more interest. This will accrue interest. And then you're going to make another payment of R dollars, right? So I think you can kind of see the pattern here. At the end of the fourth payment period, this one will accrue more interest. This one will accrue more interest. This one will accrue interest for the first time. And then this one is a brand new payment that you're making at the end of the fourth payment period, and so forth. So the pattern is, at the end of n payment periods, this is how much money is going to be in the account. That's kind of a nasty formula. The good news is that we can handle this kind of thing. So the future value F is going to be this sum. We can factor out the R, and that leaves us with this stuff. And now here's the crazy thing. This kind of sequence, 1 plus R over M, 1 plus R over M squared, 1 plus R over M cubed. If we just call 1 plus R over M A, then this is really one we could call a to the 0. So it's like a to the 0 plus a to the first plus a to the second plus a cubed and so forth, all the way to a to the n minus 1. This is what's called a geometric series. And we happen to know how to add up the terms of a geometric series. We have a formula for that. It's a to the n minus 1 over a minus 1. So in this case, a is 1 plus r over m. So if you just take this formula, you get 1 plus r over m to the n minus 1 divided by 1 plus r over m minus 1. The positive one and the negative would cancel, giving you that. And then finally, we're going to replace n with mt because after t years, there will have been m times t payment periods, because we're assuming that this is a simple annuity. Okay, so the number of payment periods is equal to the number of compounding terms in the year. Okay, so putting that all together, this is the formula, right, for the future value of an annuity. So if R dollars are deposited at the beginning of each of m payment periods per year into an account with an annual interest rate R, then the amount in the account, F, after t years is given by this formula here. Okay, which looks complicated, but it's a lot better than than this, right? So let's practice using this thing. So example 1 says, in planning for their retirement, Lucy and Antonio consider setting up a simple ordinary annuity of $50 per month at an annual rate of 3%. Calculate the future value in 15, 20, and 25 years. Okay. So the future value after 15 years is going to be the rent, right? The monthly payment R. So the rent, $50 times 1 plus R over M to the MT. That's pretty standard, right? We're used to working with that kind of thing. 1 plus R over M to the MT. So 1 plus interest rate is 3%, so 0.03 over M is the number of times it's compounded each year. In this case, they're depositing $50 per month, so M is 12. So that's 1 plus R over M to the MT, so 12 times 15 years. Okay. Minus 1 divided by R over M. So minus 1 and then divided by R over M, 0.03 divided by 12. Okay. So let's punch this into our calculator ever so carefully. If you wanted to do this one piece at a time, you could. For example, you could do 0.03 divided by 12, get the answer, and then add 1 and get that answer. And then you could do 12 times 15 and get that answer. And then you could take this answer and raise it to that answer, right? Then you could subtract 1. Then you could find this 0.03 divided by 12. You can find that answer, divide this part by this part, and then you can multiply by 50, right? So what I'm saying is you could do this one piece at a time if you'd like. I'm going to go ahead and throw the whole thing into my calculator at the same time, and I'll show you how I do that. So I'm going to do 50 times. I'm going to open up a set of parentheses like that. And then I'm going to do another set of parentheses for the numerator of this fraction. And another set of parentheses for the denominator of that fraction. So the numerator of the fraction is going to be, I'm going to open up another set of parentheses. 1 plus 0.03 divided by 12. And I want to raise that to the power of 12 times 15. And then I want to subtract 1, and that's the numerator. The denominator is going to be 0.03 divided by 12. Okay? And then in my case, my calculator is really nice, and so I can see, I can look at what the display is, so I can tell that it was displayed correctly. I can tell that it went in there correctly. By the way, if you use the Google calculator, so just Google like calculator, and it'll allow you to do kind of the same thing, I think. But anyway, there you go. There's the future value. So after 15 years, they will make $11,348.63 approximately. So that's after 15 years. After 20 years, everything stays the same except for the number of years. So this 15 right here is going to change to a 20, and everything else is the same. 50 times 1 plus 0.03 over 12 to the 12 times 20 minus 1 over 0.03 over 12. And so in my calculator, I'm just going to come back here, and I'm going to change the 15 to a 20. That's $16,415.10 approximately. Okay. And then after 25 years, everything stays the same. Except for the 20 becomes a 25. So the 20 becomes a 25. $22,300.39. Okay. Now, you may be interested to know, like, well, how much did the interest rate help us here? Because they were putting in $50 per month for 15 years. So you could figure out how much that would be if they just like put this in a, like, if they just took out the cash and put it underneath their mattress at home or something, right? Like, how much cash would they have had? They would have had $50 times 12 months per year times, in this case, 15 years. That would have been $9,000. But you see, by investing it, they're able to get over $2,000 more than that. And if it had been 20 years, then the discrepancy is even larger, right? $12,000 if they just stuffed the cash under their mattress versus $16,400 if they invest it. And then $25, or 25 years, sorry, would be $15,000, whereas if they just stuff it under their mattress, whereas they get $22,300 if they invest it, right? So that's the power of annuities, right? So not a bad idea. And I think you could actually find an annuity with a 3% annual rate. So imagine, I mean, it's like, at this point, we're talking about an additional $7,300, right? That's this amount and then half that amount again added back to it. It's like 150%. It's like an effective rate of 150%. So that's pretty good. Anyway, let's look at another example. This one says, Mr. Koluski wants to set aside money in a sinking fund at 8.5% annual interest with quarterly payments to buy a $35,000 yacht in 10 years. How much rent must he deposit each quarter? So let's see. I think my kids need my help for something. So hold on a sec. My kids wanted to watch a video, and it was so urgent that they had to come interrupt me in the middle of recording a lecture. Anyway, so this guy wants to buy a yacht. He wants to save up $35,000 over the course of the next 10 years so that he can buy a yacht in 10 years. Okay. He's going to put his money in a sinking fund at 8.5% annual interest. That is a good interest rate. Well, he's going to make quarterly payments. And the question he wants to answer is, how much does he need to deposit each quarter, right? What's the rent going to be? So, okay, so we know that he's going to be doing this for 10 years, so T is 10. We don't know what the rent is, so we'll just leave that R for now. But it's going to be R times 1 plus the interest rate, 0.085, divided by the number of times the interest is compounded per year. If he's depositing quarterly, then that's going to be 4. To the 4 times T, T again is 10, okay, minus 1, divided by 0.085 over 4. So we can solve for R because we know that this needs to be he needs it to reach $35,000 in order to be able to buy the yacht of his dreams, I guess. Okay, so I'm going to punch this stuff into my calculator, right? So I'm going to do 1 plus 0.085 divided by 4 to the 4 times 10. Then I'm going to subtract 1, and then I'm going to divide that by 0.085 divided by 4. So that's 62.06 blah blah blah. Okay, and so then to solve for r, I can divide by 62.06607. And we get r equals 35,000 divided by that number, which comes out to about 500. It comes out to about $563.92. So that's how much he has to invest every quarter. That means like every 3 months, right? So once every 3 months, he needs to make a $563.92 deposit into this sinking fund in order to be able to afford his yacht in 10 years' time. Now, how much money, I wonder, how much money is he actually going to put into the account in order to get this amount of money? It's not going to be $35,000, right? It's going to be 563.92 times, if he does this quarterly, then that would be 4 times per year. So I'm going to say times 4. And he wants to do this for 10 years, so times 10. And that equals $22,556.80. So he's going to put in $22,556.80 of his own money. And over the course of the 10 years that it's in this sinking fund, it's going to turn into $35,000 that he can use to buy his yacht. So once again, if he just sticks the cash under his mattress, this is what he gets. If he invests it, this is what he gets, right? So so pretty smart if if he's trying to buy a yacht to do it this way. Okay. One more example. It says the Jacoby County School Board wants to have $750,000 available in 8 years to build a new elementary school. The board considers 2 possible sinking funds. One can be arranged with semi-annual payments at 6 3/4% annual interest, and the other with quarterly payments at 6 5/8% annual interest. Which of these funds would cost the board less money annually? Okay. So this one, the 6.3 or 6, it would really be 6.75, right? So this one, I'm going to call Fund 1, maybe. So Fund 1. So the semi-annual payments at 6.34% annual interest. I'm going to call that Fund 1. And then the quarterly payments at 6 5/8% annual interest, I'm going to call that Fund 2. And I'll deal with Fund 2 a little bit further down. Okay, but let's look at Fund 1. Let's figure out how much money are they going to end up putting into Fund 1 each year versus how much money they're going to put into Fund 2 each year. So let's see. For Fund 1, They want the future amount to be $750,000 in 8 years. So we'll say future value after 8 years is going to be the rent, which we don't know yet, times 1 plus interest rate, 6.75%, so 0.0675, divided by number of times it's compounded each year. If it's compounded semi-annually, then that means it's compounded twice per year, to the 2 times the number of years, which is 8, minus 1, and then divided by 1 plus 0.0675 over 2. And they need that to equal $750,000. So let's see. So I'm going to punch this stuff into my calculator. So I'm going to do 1 plus 0.0675 divided by 2 to the 2 times 8. Okay, then I subtract 1, and then I divide by 1 plus 0.0675 divided by 2. Actually, is it a 1 plus? No, it's just the, so I don't need this extra 1 plus. It's just the 0.0675. Okay, so that's, 20.7 whatever. Right, so I get R times 20.763877 and some change. That equals $750,000. So if I want to solve for the rent, R, then I need to divide by 20.763877. And I get R, R equals 750,000 divided by that number. So R is about $36,120.42. Right? This is how much they'd have to deposit semi-annually. So that's twice per year. So so they'd have to deposit this semi-annually. Right? So in 1 year, this costs them 2 times R, right? So that's 2 times $36,120.42. So I'm going to say 2 times 36120.42 is $72,240.84. And I'm almost out of room on the page, but there you go. $72,240.84. That's how much Fund 1 would cost them. Now, if they put that much in there each year, then at the end of 8 years, they're going to have $750,000, which is pretty good, right? Because if you imagine, even if they did this for 10 years, if they just stuffed the money under their mattress, right, that would still only be $720,000. That's if they did it for 10 years. But in 8 years, they're going to get all the way to $750,000 because they've invested it in this annuity, right? Or they've set up the annuity, I guess. They've invested it in that sinking fund. For Fund 2, f of 8 is going to be R times 1 plus, so the interest rate here is 6 5/8%. So 5/8 is about, it is 6.625. So 6 5/8 would be 6.625. As a decimal, that would be 0.0625. Right? So it's 1 plus that divided by, now they're going to make quarterly payments, so we're going to divide that by 4 and raise that to the 4 times 8 minus 1 divided by 0.0625 over 4. And that also needs to equal $750,000. So let me punch this into my calculator now. I'm going to have 1 plus 0.0625 divided by 4 to the power of 4 times 8. Then I'm going to subtract 1. Then I'm going to divide by 0.0625 over 5 over 4. And I get 41.11101, blah, blah, blah. So this is R times 41.1110124. Okay, that needs to equal $750,000. So now to solve for the rent, we would divide by 41.1110124. And we would get that R is approximately 750,000 divided by that number, which comes out to $18,243.29. Now, at first glance, that seems good. That seems like a lot less than that, right? But keep in mind, this one they only have to pay semi-annually, so they only have to pay it twice per year. This one they have to pay quarterly, so they have to pay it 4 times per year, right? So they have to pay this amount quarterly. So how much is it going to cost in 1 year? Well, so in 1 year, this costs them 4 times R, right? Which is 4 times $18,243.29. So this is going to be kind of a close call, I think. But now I'm going to multiply this times 4, and I get $72,973.15. Okay. So now we can compare the cost of these two funds to see which one's better for them. So this fund is going to cost them $72,240.84 per year. This one's going to cost them $72,973.15 per year. So clearly this one is the cheaper fund. Okay. Not by much though. I guess it saves them, about $700, maybe $600, $650, something like that. Anyway, so it doesn't save them very much. When you're talking about like $70,000 already, an extra $600 is kind of chump change at that point, right? But still, it's helpful to go with the cheaper option. So which of these funds would cost the board less money annually? Fund 1. So Fund 1 costs less money annually. And that's that. That one was a doozy of a problem, right? But good to know. Good to know that you can kind of piece all this stuff together. You have the tools to do it now. So we're almost done talking about finances. In lecture 20 is going to be the last lecture of this unit of material, and we'll talk about loan amortizations. So for like your home mortgage or for your student loans or whatever, right? So that's that for now.